In this lesson, we're going to talk about approximate numbers versus exact numbers, and then we're going to go on to talk about something called significant figures. And approximate numbers are numbers that are determined by measurement. Exact numbers are determined by definition or counting. So, for example, if I wanted to measure the length of my math textbook, when I measure something, that would be considered an approximate number, because if I measure it and I get that it is 11.3 inches in length, and then another person measures it, they might get 11.5 inches in length. So measurement may be different from person to person. It also might determine on the tool that you're using to measure. And it also might determine the person's preference on how to round. So when you're measuring something, it's going to be considered an approximate number versus an exact number. If you have, say, a list of names on a piece of paper, if you have 12 names, then you're just doing that by counting. You're determining the number 12 by counting, and there is exactly 12 names on there. Or if you want to talk about something, a number that is exact by definition, you can say that there are 12 inches in a foot. So 12 is an exact number because it's determined by definition. There are exactly 12 inches in 1 foot. So here are some examples where we can determine whether it's approximate or exact. So in example A, says the number of cookies in your packed lunch. So that would be determined by counting. So that would be an exact number. The radius of the planet is 2,428 kilometers. That we would have to determine by measurement. So that would be considered approximate. The blackboard in the mathematics classroom is 49 inches long. That we would have to also determine by measurement. So that would be considered approximate. And then in part D, the number of eggs left in the carton. That we would have to determine by counting. So that would be considered an exact number. When you're rounding approximate numbers, you want to make sure that you capture the most interesting or the most important digits based on the circumstances and how accurate you want to be with your measurement. And so these number of digits that are called the important or the interesting digits are called the significant digits. And we have some rules for being able to identify which digits are significant. Trailing zeros and a decimal are significant. And what we mean by trailing zeros and a decimal are the ending zeros to the right of the decimal place. So these are considered significant because it tells us something about the accuracy of the measurement being made. So for example, 4.20 is equivalent to 4.2. But when it comes to the accuracy, by putting that zero on the end, that tells me when it was rounded that the number to the right of the zero had to have been 4 or less. Versus if I look at just the 4.2, we don't really know anything about the digit to the right of 2. Because 4.2 could have been 4.17 rounded to 4.2. So by putting on that zero on the end, that tells us it was specifically rounded to the hundredths place. So we know that the digit to the right had to have been 4 or less. The next rule is zeros between non-zero digits or other significant zeros are considered significant. So, for example, the 4002 has 4 significant figures because these two zeros are between 4 and 2, and 4 and 2 are significant digits because they're non-zero digits. Here we have 3 significant digits because the 0 between the 3 and the 6 is counted as significant. And then this 0 here is considered significant because this 0 here is considered significant because it's a trailing 0 to the right of the decimal. And this is a non-zero digit, so that's 3, so that's considered significant. And since this middle 0 is between 2 significant digits, that middle digit is considered significant. Now, leading zeros, meaning zeros to the left of a decimal, are not considered significant. Those don't tell us how the number was rounded or the accuracy of the number. The number in 0.006 that's considered significant, that tells us how it was rounded, is the 6. So in that decimal, we only have one significant digit. And the same thing goes for this second example, the 0.00052. The 2 is what tells us how it was rounded. Okay, so then the last one is trailing zeros in a non-decimal are not significant unless stated otherwise. Meaning trailing zeros in a whole number are not considered significant because it doesn't tell us how it was rounded. It just tells us that it's accurate to the 10,000th place. And so in the number 40,000, we only have one significant figure. And then in the 210, since this 0 here is a trailing 0 in a whole number, that's not considered significant. So the 2 and the 1 are the only significant digits in that number. Okay, in this example, we have 3 parts. We're going to identify the number of significant digits. So in example A, we have 68,000. Trailing zeros in a whole number are not considered significant. So in this example, only 6 and 8 are significant, so this is considered 2 significant figures. In example B, we have 1.09040. Of course, all the non-zero digits are significant. And then when we look at the zeros, this 0 is considered significant because it's between 2 non-zero numbers. This 0 is considered significant because it's between 2 non-zero numbers. And then this digit is actually considered significant. It's a trailing 0 in a decimal, which tells us about the accuracy on how it was rounded. This tells us that it was rounded 1, 2, 3, 4, 5 places out. So in this case, we have 6 significant figures. And in part C, we have 5,000.5. And because these 3 digits here are between 2 non-zero digits, those are considered significant. So in part C, we have 5 significant figures. Okay, in the next couple examples, I'm going to show you how to round with significant digits. So in part A, it says take 8518 and round to 3 significant digits. So since we want 3 significant digits, we're going to look at the first 3 numbers, and we're going to round that to 8520. And we're bumping that 1 in the tens place up to a 2 because that 8 is 5 or bigger. And now when we look at this, we have 3 significant digits. 1, 2, 3. Because this 0 is a trailing 0 in a whole number, it's not considered significant. Okay, in the second example, it says round 13.66 to 2 significant digits. So I'm going to look at these 2 digits here, and I'm going to rewrite that as a 1, 4, I'm going to rewrite the 3 and bump it up to a 4 because that 6 is 5 or greater. And now we have 2 significant digits. Be careful, if I write it like this instead, now this is considered 3 significant figures. Although the value of 14 and 14.0 is the same, they have different meanings when it comes to significant figures. Because I made a 0 here, that would tell me I would have 3 significant figures because trailing zeros after a decimal are significant. Okay, so now we're going to talk about precision versus accuracy. When we talk about precision, we refer to the number decimal values. And so the more decimal values you have to the right of the decimal, the more precise your number will be. So for example, if I gave you 3.14 and I gave you 3.1415, this number here would be more precise since we have more decimal values. Now, when we talk about accuracy, we refer to the number of significant digits. So the more significant digits we have when we approximate a number, the more accurate that number will be. So for example, if I gave you 14.93 and then I gave you 14.930, this number here would be considered more accurate because this number boxed in red has 5 significant digits, whereas the 14.93 only has 4 significant digits. And this number here, I'm including 0 as a significant digit because it's a trailing 0 to the right of the decimal. So in these examples down here, we're going to list which one is more accurate and which one is more precise. We're going to first list which one is more accurate and then the one that's more precise. So we're going to do that for each one. Okay, so for the first example, we have 14.9 and we have 0.67. Now, 14.9 has 3 significant digits. 0.67 has only 2 significant digits. So x is 14.9 is the number between those two that is the more accurate. Now, because the 0.67 has 2 values to the right of the decimal, and x only has 1 decimal place to the right of the decimal, then y is equal to 0.67 is going to be more precise. So a number that's more accurate is going to have more significant digits. Let me put that in parentheses here as a reminder. And a number that's more precise has more decimal values. Okay, in the next example, we have x is 0.4 and y is 14. Y is 14 has 2 significant digits, and x is 0.4, only has one significant digit. So y equals 14 is going to be more accurate, and since x is equal to 0.4 has more digits to the right of the decimal place, 0.4 is going to be more precise. In the last example, part C, we have x is 6,000 and we have y is 0.0050. X is 6,000 only has one significant digit, and y is equal to 0.0050 has two significant digits. That's these right here, because trailing zeros to the right of the decimal count as significant digits. And y is equal to 0.0050 is actually more precise as well, because there's 4 decimal values to the right of the decimal. So in this case, y is equal to 0.0050 is more accurate and more precise than x is equal to 6,000. Okay, now let's talk about operations with approximate numbers and significant digits. And I want to stress that this is for approximate numbers. There's a different rule if you have some exact numbers in there, and we'll get into that next. But for right now, these are the rules specifically for approximate numbers. So if you want to add and subtract approximate numbers and you care about significant digits and accuracy and precision, the rule that you want to follow is you want to look at the precision of the least precise number in the problem, and that is what you're going to use to round your final answer. And so remember, precision is focused on the number of decimal places. So if you look at the example we have here, I have 73.2 plus 8.0627, and when we add that up like we normally would on our calculator, we would get 81.2627. So if you look though, when we want to write our final answer, here we have 1 decimal place, and here we have 4 decimal places. So I want to make sure I look at the least precise number. And 73.2 is the least precise number because it only has 1 decimal place. So that means I want to round my answer to only 1 decimal place. So even though this is the answer we get on the calculator when we add it up, if we want to round it using precision and accuracy, I would round it to 1 decimal place for my final answer. Now, with multiplication and division, you want to use accuracy. Remember, accuracy relates to the number of significant digits. So when you look at a problem that has multiplication and division in it, you want to focus on the least accurate number, meaning the number that has the least number of significant digits. So if I want to take 41,500,000 and divide by 82,000, if you notice, here I have 3 significant digits, and here I have 2 significant digits. So if I look at the least accurate number, that's the number that has the least number of significant digits, so that would be 2 significant digits in this example. So when I round my answer, I want to make sure I round it to 2 significant digits. So when I take on my calculator and I take 41,500,000 and divide by 82,000, that gives me 506.10. And so I want to make sure I round it to 2 significant figures. Because this is multiplication and division, I'm focused on the accuracy rather than the precision. And if you have a calculation that has multiple operations in it, you want to make sure you keep track of how many significant digits you do after each step, and wait till the very end to round. So you follow the steps and the rules for each operation, and then you round at the end. Okay, now let's do some examples that do have multiple operations in them, and these are still with approximate numbers, so we're going to use the rules above in the chart that we just went over. Okay, so example A, we're going to take 0.473 plus 1.3, and then subtract 16.08. Now this is all addition and subtraction, so if you look at the chart above at the rule, when we're doing addition and subtraction, we want to focus on precision. which means we want to look at the least precise number, which focuses on the number of decimal places, and then use that number of decimal places to round our final answer. So if I were to add this on the calculator, I would get negative 14.307. And then to figure out how to round it, I have 3 decimal places here, 1 here, and 2 here. So because this is based on precision, I want to look at the least number of decimal places we have and use that to round. So since my least number of decimal places is 1, I want to write my final answer as negative 14.3. Okay, in the next example, we have 8.9742 times 22. And this one is slightly tricky. Because this is multiplication, I want to make sure that I'm focused on accuracy, and I want to make sure that I keep the least number of significant digits in my final answer when I round it. So if I do this on the calculator like I normally would, I would multiply this and I would get 197.4324. That's not the tricky part. The tricky part now is noticing that here I have 5 significant digits, and here I have 2 significant digits. So I want to round this with 2 significant digits. So I want to round this up to 200. But the problem is if I leave it like that, that's only 1 significant digit. So I then have to rewrite it in a way so I have 2 significant digits. So if I look at it, I would have to write it like this in scientific notation so that it indicates that I have 2 significant digits. Because remember, trailing zeros after a decimal place is considered significant. So if I write it like this is considered 2 significant figures, versus if I write it like this would be considered 1 significant figure. So that's why this one's a little bit tricky, because we have to write it in a way so that we have 2 significant figures. Okay, now in this example, we have mixed operations where we're going to mix our rules. We have division and we have addition. And so using order of operations, of course, we do this first. So when I put that in on the calculator, I get 0.0131126554. Because that's division, I want to use the division rule where we focus on the accuracy, which means we're focused on the number of significant digits. The 0.0717 in the numerator has 3 significant digits, and the 5.468 in the denominator has 4 significant digits, which means I don't want to round yet, but I want to keep in mind this number here, the 0.01311 number, should be rounded to 3 significant digits, which means I need to keep 0.0131. And now we have to take that and add it to the 0.0636 number. Now, again, I want to stress you don't want to round until the end. You want to keep track of what numbers you have where you're rounding, but don't actually round it until the end. Now that we're using addition, we want to go to the precision rule. So I have 3 significant digits for this number here, but that gives me 4 decimal places. Right, 0.0131. That gives me 4 places because we're focused on precision now with the addition. And then for this number here, I have 4 decimal places. So in my final answer, when I add that up, I should have 4 places. So I'm going to take my 0.01311 number, but the whole thing, we don't round until the end, and then we add it to the 0.0636 number, and the answer that we get on the calculator would be 0.07671265554. Now with the addition, because that's our last operation, I have 4 places and 4 places, so I want to make sure that I round to the least precise number. And by default, since they're both 4 places, we're going to round to 4 places. So my final answer, using accuracy and precision, 0.0767. Okay, in this last example, we also have mixed operations. Using order of operations, I want to make sure I do this down here first. So I'm just going to carry over the 3311. So on my calculator, I'm going to do the 0.8208 times 4631. And when I do that, I get 3801.1248. And then I'm going to carry over the 1315. Now, what I did here to get the 3801 number was multiplication. And with multiplication, you want to focus on the accuracy, which means you want to keep track of your significant digits. So, in both the 0.8208 number and the 4631 number, I have 4 significant digits. I'm going to leave it there, but I'm not going to round it till the end. If I have 4 significant digits, then that means I would round it to 3801 at this point. But I wait until the end. Okay, the next thing is I would subtract. So I would take that whole number, 3801.1248, and subtract 1315. With subtraction, we're focused on the precision, which means we're looking at the least number of decimal places. Since I rounded this in the back of my mind to 0 places because I just want to keep the number 3801, and this has no decimal places, then when I write my answer down here, I want to keep in mind I don't want any decimal places in the denominator of my fraction. I'm going to carry over all the numbers, but I'm going to wait till the end. I'm going to wait till the end to actually round it. Okay, so I would have no decimal places in this number. My last thing is I'm going to take the 33.11 and I'm going to divide by 2,486.1248. That's going to give me 0.01331791155. Because this is division, we're looking at accuracy, which means the number of significant digits. So if you notice, if I rounded this to 0 decimal places, that would give me 4 significant figures here. This gives me 4 significant figures. So you look at the least number of significant digits, and by default, we have 4 here. So I want to make sure when I round my final answer, I'm going to have 0.01332. Because that 7 is bigger than a 5, I need to bump that 1 up to a 2. And now I've got my 4 significant figures. And this has been rounded with accuracy and precision. And our final topic in this section is operations that involve approximate numbers and exact numbers. So the rules that we've been following so far are specifically for approximate numbers. But when you have an operation that has exact numbers and approximate numbers in it, our final answer is only going to depend on the approximate numbers for accuracy and precision. The directions are telling us that in all these examples, the second number is considered an exact number. So if I look at example A, 1.3 is going to be an exact number. So we're not going to worry about checking the accuracy and the precision for that number. We're only going to use the accuracy and precision rules with the 0.473 number. So if I put it on my calculator, 0.473 plus 1.3, I'm going to get 1.773. Now to round it with accuracy and precision, because this is addition, we're going to be focused on the number of decimal places and precision. And since I have 3 decimal places in my approximate number, I should have 3 decimal places in my final rounded answer. So 1.773 is going to be my final answer rounded with accuracy and precision. Looking at part B, I have 6.9342 times 41. When I put that in on the calculator, I'm going to get 284.3022. Now the direction says that the second number is exact, so our accuracy and precision is only going to rely on 6.9342. Since we are multiplying, we're going to be looking at the number of significant digits that we have. So in the 6.9342 number, we have 5 significant digits. So when I round it with accuracy and precision, I want to make sure that I have 5 significant digits in my final answer. So my final answer is going to be 284.30. In part C, the second number we said was exact. So our accuracy and precision is only going to rely on the 17.319 number. Since this is subtraction, we want to look at the number of decimal places. So if I take 17.319 and I subtract 36.9 on the calculator, I'm going to get negative 19.581. Well, in the 17.319 number, I have 3 decimal places. So I want to make sure I have 3 decimal places in my final answer. So negative 19.581 will be my final answer. And in the last example, I have 5 divided by 120. 120 is considered exact. So my accuracy and precision is going to rely on the number 5 only. So if I take 5 divided by 20 on the calculator, I'm going to get 0.041666 repeating. And since this is division, we want to look at the number of significant digits for the approximate number, and that would be 1. So when I round my final answer with accuracy and precision, I want to make sure I only have 1 significant digit. So my final answer is going to be 0.04.